Good afternoon, everyone. I'm Dr. Dave Altabelli. I'm a senior scientist here at Kimball Physics. And with me is Abigail LePage. She's a physicist, vice president and CEO of Kimball Physics.
Hello there.
With over 20 years of experience in the field. So we're excited to be able to give this presentation here today. At this moment, we're not really sure whether this is broadcasting out because it says speaker waiting on our screen, but I think we'll just try to go forward and see how we do. So we're going to share our screen. Host, disable, participant, screen share.
Wow.
Well, you know, maybe.
Say that. Okay, well, we can't show the slides apparently.
Okay.
Sorry.
I guess we could try to just get started talking. You know, basically, what we're going to talk about today is some of the products that we made, specifically this MCF, which is a multi-port, the ConFlat Flange type of vacuum system chamber. And what we're going to do is we'll talk a little bit about this. We're going to have a series of slides to do this, and evidently we don't have access to those slides. So why don't we try to just get started, and then we'll switch over the slides when they're available. So this is what these chambers look like. And, you know, they're made out of either stainless steel or titanium, and there's a lot of thought and innovation that goes into these designs. Now, let's talk a little bit about Kimball Physics. Kimball Physics is a high-tech manufacturer of scientific instruments. We have over 50 years experience. We just went through our 50th anniversary, and we have a lot of experience in ultra-high vacuum electron and ion optics. Our company specializes in high-stability electron emitters, precision electrostatic and magnetostatic optics, along with state-of-the-art vacuum chambers and fittings. Electron and ion systems are optimized for beam energies in the range of from 1 EV to 100 keV and beam currents from femtoamperes to milliamperes. So we have a broad range of products that include electron guns, ion guns, these vacuum chambers that we're going to spend our time talking about today, as well as several types of cathode electron emitters and detecting type systems, as well as supporting parts that we can use to mount and position different apparatus and devices inside these chambers. Let me just check and see if we can get to our slides again. No, can't get there yet. Okay. Now, Kimball Physics was founded by Professor Chuck Crawford. He was an MIT professor at the time, back in 1969. Matter of fact, he was a full professor, and I think he was one of the youngest full professors ever at MIT.
I think so.
And so this company is an MIT spin-off company, and Dr. Crawford, he likes to be called Chuck, saw the need and the opportunity to advance the field of ultra-high vacuum electron and ion optics, and specialized specifically in high-stability electron emitters, you know, precision electrostatic and magnetostatic optics, along with these vacuum chambers. And what he really did was see a unique space that could be filled by these chambers, because, you know, as this talk is about, we didn't just decide that, hey, we needed to make chambers. There was a need for a chamber that was compact, efficient, precise, and that's how this whole product was born. So our products have done a lot of things, including going into space for advanced physics experiments. We've won, you know, numerous awards and hold several patents with these products. And our products are all over the world in major universities, research labs, and commercial enterprises. So we're very proud and excited to be able to bring this to you today. Our mission is to advance humankind by doing good physics, and specifically electron optics and vacuum physics, and all the while growing and being good citizens, making a living, and of course having fun along the way. We have, you know, we're in a remote location in southern New Hampshire, and we're basically a half dozen buildings on a nice, beautiful wooded hilltop in southern New Hampshire. And the company is run by physicists, and it's ready to assist customers not only with providing these existing products that we have, but solving practical, technical, and basic research problems that you have. And so it's great that we have the opportunity to present at least part of our presentation to you guys today. So we really encourage collaboration with scientists developing new technologies, and that's strongly encouraged. And a good part of what we do is involving custom type work. So what we do is we provide, let me just see if we got slides yet. No, not yet. So we provide integrated systems and components for ultra-high vacuum electron and ion optics. And we specialize in high stability electron emitters, and as well as what we mentioned earlier. Many of our research grade and OEM electron and guns and MCF chamber designs have been inspired by the unique challenges of our customers. So one of our product lines that we are very excited about, and it's been around for really a long time, and that's actually where we have several of our patents, involves essentially these vacuum chambers and the mounting hardware associated with those that can be applied to ultra-high vacuum applications where there are spatial constraints and where there often is a high density of experimental apparatus that's required. And to be able to achieve these, ultra-high vacuum or UHV type performance, what we really need is to minimize both the macroscopic and microscopic surface area of the interior parts of the chamber. And the way we do that is by having some highly polished surfaces, which are, when you see a chamber, it's very distinctive that they know that it's simple physics. And all the interior surfaces are contoured and very smooth. There's no nooks and crannies in there. And there's minimal welds. So most of our signs are actually made from a single block of material. And the flange, the ConFlat Flange, which is the way that we're able to join and attach different accessories and other chambers, is a proprietary design that came out of the early 60s by William Wheeler, I think his name was.
Yes, Bill Wheeler.
Bill Wheeler. And basically the basis of a ConFlat flange, for those who don't know, is that there's an area where the seal can occur that's slightly recessed below the surface of where the bolt holes are. And in there's an annular knife edge that goes around there. And what's done is a piece of copper, a ring of copper is placed into that space. And then on the mating part, it also has another knife edge type of edge. So when we tighten those two parts together using these bolt holes, what happens is the knife edge will impregnate into the surface of the copper, and the copper will deform and flow to create a very microscopic seal that can be created with this part. And so I think the insight that Dr. Crawford had with this whole thing is that this sealing arrangement didn't need to be this annular disc that was welded to some other structure. That sealing surface could actually be integrated totally into the block, the monolithic metal that existed. And by doing that, and what happened is a couple of things came along that made that possible. At the time, CNC milling capabilities and solid modeling capabilities were becoming more available. And as Chuck liked to say, this MCF chamber was the product of physicists running amok with 5-axis CNC machines.
Right, inadequately supervised physicists, no less.
So really with that technology coming along and being accessible and really seeing the need that, okay, these don't need to be separate lathe fabricated flanges. We could actually put the surface of the flange directly into the chamber itself. And what that allowed us to do is to become very much more precise in what this, is that high enough? Yeah, it shows up here. So it would be much more precise with how we can position these. Matter of fact, these are within tolerances of, tens of thousandths of an inch and 0.1 degrees of axial alignment here. So, all right, let's see, what else did I want to say about these? You go on to the next.
One other thing I just want to add, given the title of this workshop being, that this product line has come out of necessity, it looks like we're actually behind on the timing.
Oh, it actually goes up there. Wow, that's a lot. Okay.
But anyway, necessity is what created the product line. And really, it started with this actual part, which is our flange multiplexer. And we didn't start making flanges and chambers. Kimball Physics started making electron sources and electron guns. And for those of you that have seen our electron guns or anything similar, you know that there's a number of electron optical elements that have to be attached with wiring that has to go through feed-throughs, and we wanted to get them all compact and coming out one end while the electron gun can insert into your vacuum chamber. And so this part, our flange multiplexer, takes 1 2 3/4 flange and mates it to 5 1.33-inch mini ConFlat flanges. And ultimately, Chuck designed a version of this part, and then he went to flange manufacturers and said, would you guys make this for us? Mm-hmm. And basically they said, no. Why would we make something that complex? There's not a real need. And so, well, that doesn't go over too well with physicists. So what we did is we said, well, I guess we'll just make our own. And so this then leads to, oh, well, we could do this, and we could do this and this. And so the product line just kind of grew out of that necessity for what we thought was a need. And now, others in our community, our scientific community, I think also have the needs.
Well, I think what kind of indirectly came out of this was that, okay, we had this new technology we could use with solid modeling and 5-axis CNC technology. And so indirectly what came was just a more efficient device, because what happens is we're able to put the same useful volume into a much smaller volumetric space. And so by making this is machined from essentially one piece of stainless steel or one piece of titanium, and by doing that, we're able to essentially optimize the usable internal volume that's in this chamber, as well as reducing the external footprint as well. Because Chuck would say, lab space is not cheap. You don't want to take up too much space. Mm-hmm. And so that's incredible. A lot of the other benefits that came from this. So it's often can be lighter. It's got more rigidity because it's really the most efficient use of the material that you could possibly do with this type of system. You're able to create the different diameters for the ports by essentially how far you move in. Because let's imagine this started as a sphere, both with an outside and inside diameter. And then what happened is, as we create that ConFlat surface, obviously a bigger port would have to move in closer, and the smaller ports would stay farther out from the center of the radius. And it was just a great way to bring together a lot of ports into a very compact area. And we didn't have to waste a lot of space to be able to take the flange and essentially attach it to the core chamber that was there. Mm-hmm. And obviously in this whole area of UHV, the more useful, efficient use of that space is what we're really shooting for here. So,
right, you don't want to have to pump out any more than is necessary. Basically.
Exactly. And for it to be a monolithic piece of structure of material, we don't have all these welds inside there. So obviously, if we're trying to pump out of space, minimize essentially our internal surface area and these nooks and crannies that could hold onto water and gas and other things when we're trying to achieve these high vacuums, we can essentially minimize those types of issues. Now we do have some chambers that have some welded joints, and when we do weld, we actually weld from the inside, so there's no interstices, there's no spaces that can be present there. So the bottom line is by, oh, there's one other thing that was really very important here, and that is the standard ConFlat flange is usually described by its external diameter. So let's say, what's this diameter of 2
It would be
3/4?
a 2 3/4 would be the typical.
Right. So usually we don't talk about the inside diameter of these ConFlat flanges, but normally, let's say this one was this the 2.9.
I think you're talking about the 4.5.
All right. So let's pretend this was 4.5. So this would be 2.9 on the inside. For us, but normally it would be 2.38. So what we were able to do is in Chuck's design of this, he was able to actually open up the inside diameter of each of these ports for free. There was nothing, we didn't lose anything. We didn't lose any structure.
Except for more material.
More material, right. But it gave us, obviously we could increase the conductance when we're trying to pump out the space. And believe it or not, going from a 2.38 diameter to 2.9 diameter gives an increased conductance of 50%, 40 to 50%, I think is what we calculated. So, so that came along as well with the system. Now, I think one of the things that we're most excited about, and probably not as many people even know about, is that obviously you got to put something inside this chamber. Okay, it's not going to just sit there by itself. So every single port, except on the smallest ones, the 1.3 ports, have grooves, and these grooves go around the circumference of the port internal aperture. We call these grooves or grabber grooves, and what they are is they're internal mounting structures that can be used to attach various types of materials, and structures and devices and things, and put them on the inside. So we call these groove grabbers that hold on to this, and these are grabber grooves that are held on by those fixtures. And essentially, every one of these ports will have those grooves in them, and I can kind of maybe help you see that. So that's what they look like, and that really gives an incredible versatility to this whole system. I'm going to just kind of go off track a little bit. So what we do is we also have a whole arrangement. Let's do it right here. So by the way, you can see as I'm picking this up, this is the stainless steel, and you can see I've got more inertia trying to move that. This is titanium, about half the weight. So when we can make these chambers, they're standard in stainless steel, but they're also available custom in titanium.
It's one of our favorite things to do when we're in real life, is to have people, hold each chamber and figure out what's the difference between them.
Right, we have a look, because when you look at them on a table, they look almost identical. You can't tell the difference in the reflectivity or the color or anything like that. But when they go to pick them up, there's just a big, just big smile on their face. So this is this is looking at that grabber groove, and this is just one of the devices to be able to hook onto that. So I'll just kind of take this up. We'll disengage it, and the way that looks is something like that. So it's just kind of the reverse of the grooves that are actually in the aperture of this port. And these can come over, and you can also notice there's little screws in there, little set screws. So it's not that we're just kind of positioning that in place, but we can put that in and very tightly anchor that into place. And so that's able to, and we have this pointing out, but obviously your equipment or your devices would be pointing in to the center of the chamber, and that's a way for you to mount all your devices. So the other thing that we've got that's pretty cool is that we have almost like this little, I don't want to call it tinker toys because I'll date myself, but there's all these various parts that are available that come in a set. For example, these are some ceramic tubes with connectors and around. These are these plates that are fabricated very precisely, actually. And then other rings and things and other connectors. Well, with this erector set that we have, this EV parts kit that we sell, you can make some pretty elaborate devices. So I'm not even sure what this is. There we go.
That is basically a prototype electron gun. It's got a section back here where there is a cathode triode assembly, and then it has a lens in the center, and at the end it's got a 4-plate deflector.
Wow! So again with just tubes of ceramic, metal tubes as well, various types of connecting devices, you can create, imagine if you had to draw this up in SolidWorks and go ask a machine shop to make this, and then wait till you see what the bill is to make this. So you wouldn't be happy.
Right, and again, how this is showing a design from our Electron guns. We basically created the grabber grooves so that we could mount our own Electron gun optics off of something. Before the grooves were there, it was pretty difficult to be able to mount off of it. You had to maybe weld it on a custom tube and then mounted everything on that, but then you couldn't take things apart, and you didn't have modularity. So the grabber grooves are used by Kimball Physics every day in the lab on almost all of our products as far as Electron guns and definitely MCF. So they're user friendly.
So. So as we were saying, so we have, our chambers are available both in stainless steel and custom in titanium. And I know for some ultra high vacuum applications, what do you need to be able to achieve those types of high pressure, vacuums? Because obviously we're trying to get 10 to the minus 7th Pascal, 10 to the minus 9 core. And then there's applications now even with extreme high vacuum, which go up to 10 to the minus 12 torr. And so stainless steel works especially in our design with essentially the very smooth surface, the very soft contours, the efficient use of volume and space inside the chamber, the ability to bake these up to 450 degrees centigrade, provides, and then also the increased diameter of the ports allows it to be used very efficiently for ultra high vacuum applications. Now, if you wanted to go into more extreme vacuum type of applications, you can see where we would then want to move to something that has a little less hydrogen outgas fusion, and that's where titanium comes into play. So titanium is about about 50%, 70% better than stainless steel with the rate of outgassing.
I think if hydrogen outgassing is your limit as far as the quality of your vacuum, then I think you can achieve close to an order of magnitude better by having a titanium chamber versus the stainless steel.
Yes. Okay. Yeah, that makes sense. So, and then obviously titanium doesn't have any magnetic properties to it. Now, 316L stainless steel doesn't either. However, if there's just in manufacturing some work hardening that could occur during the manufacturing process, it's possible that it could have areas that are magnetic, but it's intended not to be magnetic. But titanium clearly can't, have.
It's mostly non-magnetic.
That's right. That's right. So, all right. So without our slides, we've kind of covered most of what we wanted to do. Let me just go down through the slides that I see, if we left anything out or not. So you can imagine that if we're going to be making these chambers, then we need to be able to also make accessories that attach to it. And Abigail showed you some of those multiplexers that we make. I think one that's really, really interesting, Owen, you didn't bring this up, is that we have the number of holes that are in this ConFlat Flange pattern are actually double density. And the reason that we have this double density is, a number of reasons. One, it gives redundancy, heaven forbid a bolt breaks off in there. But second, what it allows us to do is to use a close coupling device like this. So if you wanted to essentially make two of these chambers close to each other, by having this device like this, which has essentially the same pattern as the bolts on the base, we can essentially line this up 12 to 12 here, but then on the other other device, we can go to the 1 o'clock position, and so we can maintain an orthogonal position. It's so heavy though.
I know.
We can maintain an orthogonal position with that closed coupler side. And the reason that's possible is because we have a double density bolt pattern around the circumference there. So that's
we did get a question about the titanium knife edge and how it holds up. And we've done quite a bit of testing on it, and we haven't had issues with the knife edge and the copper gasket joint. Some customers have had issues after baking that if you're using standard flanges along with titanium, that difference in thermal expansion can cause issues where you then have to tighten up all the flanges after baking. So the best combination is titanium flange to titanium chamber. Not that that's always
Right.
criteria if you're not baking.
Now, can you use a copper rings with titanium steel?
You can.
You can, yeah. All right, let's see if we get any other questions. Go ahead there.
Oh, how long to machine the part that you're holding in hand? I have no idea, actually.
I don't. We actually want to get some great video footage of the machine running so that we can use that. Because I've seen 5-axis milling machines with other parts that I've worked on, and it's an amazing process to watch. No, we don't know the time for this, but then after this has been machined, obviously we then need to polish this, and we have this isn't electropolished. This goes beyond electropolished, and we use a mechanical proprietary technique to essentially get to a mirror finish. So that's a lot of work, and we think it's important for the ability for this to function as a UHV type of fixture, and I think it also gives a distinctive appearance to our products.
So another question that we did have is, what materials do we make the chambers out of? And so basically, stainless steel 316L and titanium are our major materials that we use. We have had instances where we've had customers ask for different film coatings on the inside. We've had chambers coated with a gold coating on the inside, where reactivity, some sort of chemical reaction was critical, and you had to have the gold was the least active as far as what would react with what was going on in their chamber. So we're basically always willing to listen to what the needs are and see what we can do to customize.
About any other questions? No. All right.
I do appreciate some questions, though. It means somebody's out there.
Right.
You never know.
Yeah, what's kind of weird is our screen has just said speaker waiting on it the whole time. We're fortunate the video feed is going out and we can still go forward here. And actually, it's probably more fun in a workshop to be playing with the pieces and the parts anyways, right?
Yeah.
So
you can see PowerPoints any day.
Yeah, exactly. So, all right, if there's no more questions.
Should we talk about the Octagon and the versions that we have?
Yeah, let's definitely do that, because that's a really cool concept, especially for this UHV audience. Yeah, well, we want to be able to show. I don't want to have to hold that.
Yeah, that one's. You can see us and the part.
I'll try to do it. All right, here we go. This is a unique. Well, many of our parts for customers are unique for the specific applications. So it usually starts with something that's standardized, and then we have a modification that might occur. So everyone's probably wondering, well, geez, what's this structure right here? Abigail, take that.
Right. So many of our customers in the DAMOP community would be familiar with our 6-inch spherical octagon, which has been sold for cold physics experiments for many years now. It's actually one of our biggest selling chambers. The regular 6-inch spherical octagon has 8 2 3/4 ports, which is great, gives you symmetry for laser access, and very good for atomic drafts. But a drawback has been that often our customers want to use one of the 2 3/4 ports for their pumping, and the 2 3/4 port is not very good for pumping. Actually, we did some calculations to see what we could do to improve it, and the standard 2 3/4 port with an industry standard 2 3/4 nipple, as short as it could be, would give 28 liters per second. So we looked at a few different versions of what could be done. You know, could we put an adapter on and go to a 4.5 flange, industry standard with the ID of 2.38 inches, and that improved it, but it only went to 53 liters per
So
second.
about double it or so.
So it about doubled it.
Yeah.
But then what we did is we looked at a couple other versions, and what we ended up settling on was this version where we got as large of a port that we could actually weld in. And so we've welded on one of the Kimball Physics 4.5 inch flanges, which has the 2.9 inch ID, and welded it into the chamber to get an improvement of 180 liters per second.
Wow. So from 20 to 180.
Yeah.
That's crazy.
So, you know, you may be kicking ourselves for not having designed this first, but we listened and found out that customers needed it. And so now we've got a new version of the 6-inch spherical octagon with the improved pumping port.
The thing is heavy.
I know, you're sitting there with it up. I didn't have to hold anything.
Well, I think, you know, I mean, we have so many different shapes and configurations. For example, I think this one is a 8-inch. So we go from 1.33 up to 10-inch size chambers. And usually the largest aperture is kind of what gives the chamber its size. And so in this case, we kind of have this octagon here. And essentially the octagon part comes from how many essentially ports are around the perimeter of the device. So this could be a hexagon, this could be an octagon, this could be even 10 ports. So there's different ways that we can configure this, as well as then, so this is a spherical octagon. And I think sphere comes essentially because this is based on a spherical shape, as well as the inside having a concavity that is spherical. So that's where that comes from. Versus something like this, which what we call a spherical cube. So essentially, it's kind of based on having essentially sides to it, and each of those sides will have the 2 3/4 port dimension. But you can see we can squeeze in other ports in between these. These are the 1.3 diameter ports, and so there's so many different ways that we can configure this, and with not only the size of the major port, as well as the general structure and configuration of the overall shape.
So there was a question about additive machining to see if we've been able to make even more complex structures. And we haven't researched enough to know if how good that will be for a vacuum wall. I think we'd have to do some studies on that. You know, the porosity of the part, you know, could it then be treated afterwards to then make it, you know, an interface that is good for vacuum wall. Right. We haven't explored that to this point, but it's definitely a lot of things are coming out of additive manufacturing.
And you know, there's metallic. You know, obviously it was made from a metal. You can also do ceramic, but usually metals will use some sort of a powder and sintering or welding or type technique. And unfortunately, when you pack, you know, small spheres together, you can only get them so tight. There's always going to be some space. So it's possible that something that is a low vacuum application, you know, in the kind of -4, -6, whatever it might be possible to use something like that, especially if you've got some large pumping abilities to kind of be cleaning, you know, to pulling the air and water out of those interstices. You know, maybe there's ways to coat the inside of something that's been 3D printed with a layer that's more homogeneous and contiguous so that it doesn't have that leaking. But yeah, I can imagine physicists going amok with 3D metallic printing.
You don't even want to know what would happen.
So.
I think as far as Kimball Physics goes, we've been exploring more what we could do with internal vacuum components by 3D printing, where you don't have to worry about the vacuum wall, but you just have to be concerned, will there be any outgassing? Right. And you know, mostly we're pretty interested in 3D printing ceramics. There's a lot of people doing that, and all sorts of complex geometries that are going to be possible. So
Yes, indeed. And we
run amok.
Yes. We have our own 3D printer to make some of these ceramic parts. So play with them. Yeah, I think it's going to be from what our customers need for their future projects. And the word no is not allowed, right? So,
How we say how.
Yeah, how or when is the hard question. See if you have any more questions.
There's a question, how about dissimilar materials? And I'm not sure exactly what you're talking in reference to.
Some sort of corrosion issue, maybe?
Dissimilar materials. Are you thinking about thermal expansion issues or something else? If you could elaborate.
Yeah. Obviously the thermal expansion issues are, of a concern, especially, so if we're baking this up to 450 or whatever it is to drive out the water or whatever we're trying to enhance the vacuum, if there's a major difference in those coefficients of expansion, that would definitely be an issue.
Yeah.
But I think that, I'm obviously with us, with our stainless steel and titanium systems with copper, we haven't had an issue with losing the seal with that type of bake out.
I think it depends on how drastically your bake out, or how drastic your bake out is. I actually, at the last meeting, was talking with some customers, and they weren't talking about baking to 450. They were going up to 800,
yeah.
900 degrees. And then there's definitely a problem. I think they've had a lot of failures when trying to go to those levels of bake out.
Right. So yeah, that's a good question, because let's say we tried to make with our titanium chambers, titanium rings, and titanium actually is a softer material.
Mm-hmm.
But the question is, if you've got the knife edge going into a titanium ring that has the same coefficient of expansion, but then again, maybe it's possible that, okay, we need to do something to maybe increase the hardness, maybe a titanium nitride coating or.
Mm-hmm. Right. Somehow you have to have more hardness on the knife edge than the actual gasket. And so you want to have the closest match for thermal expansion, but you also have to have it be able to really make the seal.
Right.
You can purposely work harden.
That's true.
Oh, okay. So there's a good question. Can we talk about our angled adapters for mounting laser windows? We do have flanges that are called tilt adapters, and we've got, I think, one. Well, it's not gonna be that visually stimulating, because a 1 degree tilt in a flange isn't much to see. But we've got 1 degree, 2 degree. I think we might go up to maybe even 4 degrees. So, and again, that's been based on what's the need. I think we had a couple customers concerned about the reflection of the laser and wanting to have the tilt flange so you could enter the window and have the reflection not go right back into the laser. And so we have the designs. I think they're on our website. Is that correct? Yeah. Just checking with our marketing.
Yeah.
But interested in whether that's something that you would like, or you're not finding exactly the part you need.
That would be a perfect custom application. It's it's not a big complex part, right?
Right. It's just a flange that has a conflat on both sides, but they're not parallel. They're at a slight angle. So one flange mounts to the chamber, and the other flange, typically a window, is going to mount to the other side of that adapter.
So it might be, maybe for your specific system, you have, a requirement that's not standard or whatever. But we'd be willing to look at it and see if it makes sense to custom system.
And those also have grabber grooves, by the way.
Yeah.
So then you can have the mounting if you don't have a Kimball physics chamber.
That's right, because we can put the grabber groove on.
So do we make metal glass transitions? We really don't. So one of the things Kimball Physics tries to do, we try to make what no one else is making. So if someone else is already making it, then we say, we'll buy that. So, you know, there are plenty of manufacturers that are brazing windows to flanges, and so we'll buy them. And we, on some cases, we'll have our own ceramic to metal feed-throughs, but basically that'll be because we couldn't find what we needed. No one else wanted to make it, so we make our own.
Yeah.
But still, we use outside manufacturers. We don't do our the brazing in-house.
Mhm. All right. Okay, so it looks like we're done. I want to thank everyone for, oh, we got another question coming? Awesome.
We still have maybe 10 minutes.
Oh. Sure.
We can show the whole parts. Yeah. Okay.
So I guess we got a little extra time. So let's just talk about some of the other things we make, like electron guns and ion guns as well. And you know the history why Chuck decided to, you know, how we got into this and started making these?
Well, so I mean, really, Kimball Physics started well with EV parts, but the electron sources were one of the key main products. And what you start realizing is that just making one little subcomponent isn't typically all the customer wants.
These are really small and you can't really even see them. This is well.
Yeah, but there they are.
That's right.
So once we started making electron sources for electron microscopy, it became clear that we could use our sources that were more stable than others that could be found in the market and actually build our own electron guns. We started with maybe some low energy guns to start with, and by low, you know, that depends on what field you're in, but low energy might be 1,000 volts or something in our environment. And we really we build electron guns between 1 EV or that operate from 1 EV up to 100 kEV. And so that's kind of our range of specified products. This electron gun right here is a 30 kilovolt electron gun, and it's got focusing, it's got pulsing, it's got deflection, all as either options or standard configurations. And again, most of our electron guns can kind of mix and match what options you may or may not want. So we started making electron guns, and then who wants to buy an electron gun and have to build their own power supply to drive it?
All right.
So we never intended to be making power supplies, but to make a system, we make the power supplies as well. So in order to have the high stability that our cathodes are capable of, we also have to make high stability power supplies.
Right, these power supplies have to be, you know, isolated. They need to have floating levels of voltage. You're trying to drive the deflection coils or the focus with different potentials versus the energy, which is the potential between the cathode and the anode. Then you've got obviously your grid or vane volt, which has a different potential that you need to put across it. So you can see why customers would really want an integrated power supply to be able to do all that stuff and have it stable.
Right. I don't see it.
Let's see, we had a question. We're going to see what that is.
That's metal glass transitions. Is there another one? Sorry, I'm just trying to read your question. Did you say that it was, do we make ConFlats smaller than mini?
Yes.
So we do. We do make ConFlats. We call them subminis. Right now we have to custom make each gasket because this is not an industry standard. So we haven't figured out the best production method for making those gaskets. We have made the flanges. They definitely work. They've gone through all the testing for, sealing, ultra high vacuum, and stress tests. But the problem is if we make the flange, but we don't make a chamber that has the mating flange on it, and no one else in the industry is making it, the flange isn't quite useful to a customer yet. So we need to get busy and make some chambers that have our submini flanges in them as well, so that, I mean, they're really nice. They're tiny little flanges, and you can fit them in places that you couldn't fit something else. We've actually put them in some of our electron guns where we need a window to look at the cathode so that we can see what the temperature is and be able to make adjustments. So we put them in our own electron guns, but we haven't yet really put them in the MCF line. So I think maybe because of the question, that means there's interest.
Yeah, definitely send us an email and kind of express your interest so that we can see, if it makes sense to move forward with that. Yeah, but we don't have to prove it. We don't have to pull it up.
What if people just want to hear more?
Yeah, a good tag team, right?
Yeah.
I mean, by the way, we have over, 20, at least 24 different gun designs, that from 1 EV up to 100, as well as currents from, a femto ampere up to milliamps and even amperes if we're using pulses. And so we have a broad range, and then also we have flood guns, obviously cover a broad area, as well as being able to focus down to a very small area, which I think is in the 20 micron range or something like that.
Yeah, and it's not as small as some electron guns do, but and we've been actually working on some custom projects where we're making optics to focus down even smaller than that.
Right.
So we can't help ourselves. We get into custom work because it's fun.
I think it's Now, Abigail, tell me a little bit about why you would want to use electrostatic deflection versus magnetostatic deflection in a system.
Well, there's a couple reasons. It's actually pretty simple to put in a few plates and just move the beam around.
Right.
Especially when you're talking about low energy beams or flood beams or things like that. When you get up into the higher voltages, it takes more voltage on the plate to move the beam around. And then it becomes kind of impractical to get high voltage feed throughs to be able to get enough voltage to be able to move a high energy beam. So when you get into the higher energies, you definitely want to have magnetic.
Okay.
But if you're doing just small adjustments, like correcting for astigmatism or something like that, even with the higher energies, perhaps you can have plates with low voltage just to do a little bit of shaping. One thing that's really good about electrostatic is you can move them nice and fast.
Yes.
So you're not dealing with trying to drive a coil that you might not be able to drive as fast.
Also, your bakeout can go a little bit higher.
Also, that's true. I wasn't thinking about that as a benefit, but it is for sure. And we make a re-entrant window for high resolution imaging. So we've definitely made flanges re-entrant so that the window could be into your system. So we've done that before. We don't have it as a standard product, but if you let us know what flange size you'd be looking for, we could look at what would be needed to be able to make that kind of window for you.
Oh, okay. All right,
We're getting prompted by some marketing.
Yeah, we have a prompt here. So. All right, so I think we're pretty much to the end. We appreciate you taking time with us for this presentation. Just to remind you, we have a nice website at www.kimbalphysics.com, and please visit it and look around. And also, I think our numbers to call are.
I got that one.
You got that one.
I got that one. It's 603-878-1616, and you can ask to talk to customer service, or one of our physicists or an engineer, you know, depending on what your needs are, we'll get answers for you.
Excellent. All right.
Okay, well, thank you so much for coming to this virtual new thing that we're trying. I hope it was at least semi-useful,
That's great.
even though we got a kind of funny start and you didn't get to see a number of slides, but
Yeah, you can imagine on our end when we knew we didn't have any slides and we had to just go from there.
yeah, just
Yeah.
just start talking.
Yeah. But maybe it worked out for the better. So again, appreciate everyone coming. And, just email us with any questions or thoughts and ideas for the next virtual workshop that we'll do. All right, have a great afternoon. Thank you.
Thank you.